Welcome to Summarize Science. Getting humanoid robots to walk on two legs without falling over, especially in messy, real-world environments, is an incredibly hard problem. A common approach in AI is to build one giant, complex brain to handle everything from seeing the world to moving the joints. But this paper proposes a different, more elegant idea inspired by decades of engineering and even biology. The secret, they argue, isn't complexity, but a smart architecture that splits the job into two parts, a fast control layer and a slow navigation layer. Think of it like how humans walk. You consciously decide where you want to go, looking ahead at the path, which is the slow navigation part. But you don't consciously think about every tiny muscle adjustment needed to stay balanced. That's handled by your fast, subconscious reflexes. To build this into a robot, the researchers used a clever two-stage training curriculum. First, they trained the robot's reflex system to be incredibly good at balancing, forcing it to learn by walking completely blind without any vision. Only after it mastered this did they move to stage 2 and turn on its eyes, allowing the slower navigation layer to start planning steps using the now expert reflex layer. They tested this layered, two-stage approach against the traditional one-stage method where the robot learns everything at once. In computer simulations, the results were already telling. On difficult, randomly generated stairs and uneven terrain, the two-stage layered policies were consistently more successful and stable than their one-stage counterparts. But the most dramatic proof came from experiments on a real G1 humanoid robot. They set up 4 difficult tasks: walking upstairs, downstairs, over a wobbly hinged ledge, and onto a soft, squishy ledge. The robot controlled by the single, monolithic AI failed on almost every attempt. The robot with the layered AI, however, performed beautifully, successfully navigating both the stair tasks that require careful planning and the ledge tasks that require rapid stabilization. So let's recap what this all means. The key takeaway is that for robust robot locomotion, the structure of the control system is more important than the raw complexity of the AI model. This layered approach, separating fast reflexes from slow planning, creates what the paper calls a diversity-enabled sweet spot, where the combined system is better than any single part. It's a powerful less is more lesson. This insight could make developing capable, real-world robots much more efficient. Instead of just building bigger and bigger AI, the future may lie in designing smarter, more structured systems that work more like we do.